So let's take a look at an example of an abstract vector space. Let's define L as the set of all functions that can be written as ax plus b for real numbers a and b. So for example, 2x plus 7 would be a function in this set. All right. Notice this set is going to be all linear functions. A would be the slope of the line, B would be the y-intercept, or 0b would be the y-intercept, right? So it's all uh, all the lines in R2, which is why we're using L here. It's a set of all linear functions here. So define addition and scalar multiplication on L in this way. So if I take two elements in L, two of these linear functions, and add them together, I'm going to add them together in the usual way in this case. So if I just gave you this and told you to add them together, you just add together like terms. And that's what we're doing. I'm adding ax plus cx, so I get a plus cx. And then at the end, I get b plus d. Okay, and scalar multiplication is also defined in the usual way. K times ax plus b, you just distribute the k. So my new coefficient in front of x is k times a, and then the constant term is k times b. Okay, so our question is L a vector space? Does it satisfy these properties? So let's go through them one by one. Commutative property of addition. Does it satisfy this property? If I take two vectors, two elements from L, ax plus b plus cx plus d, I know I get a plus cx plus b plus d. If I swap the order, cx plus d plus ax plus b, do I get the same thing? Well, I would get c plus ax plus d plus b. And these are equal because once we're down to this point, these are just adding numbers, right? A plus c, A and c are just real numbers. So when we're talking about adding numbers, we mean adding them in the usual way. A plus c and c plus a are just numbers, and we know addition between regular numbers is commutative. Same thing here. B plus d and d plus b are the same thing because those are just real numbers, and the addition of real numbers is commutative. So yeah, this one checks out. Okay, the vectors are commutative. What about associative? Okay, I won't draw it all out for us, but it is also associative. And we kind of intuitively know this because what are we doing when we're adding these linear functions together? Well, at the core, it's just the addition of numbers, right? It's just x is an unknown number. And we know that when we add numbers that if we add u plus v first and then add w, it's the same as adding v plus w first and then adding u. So it checks out. Okay. Is there an additive identity? Yes, there is. Yes, there is. Specifically, if I have any vector ax plus b, and I add 0x plus 0, then we know we will get ax plus b back. Okay, so that checks out. What about an additive inverse? Yep, that checks out too. If I take ax plus b and then add negative ax minus b, that'll give me the 0 vector, the 0 element. Okay? What about the distributive property over vector addition? Well, if we know how the addition of linear functions work. And so we know that this is going to hold. This is something that we've dealt with since elementary algebra. Okay. Similarly, if I take scalars and then multiply by one of these linear functions, I know that the distributive property works here. Same thing for the associative property for for scalar multiplication. A lot of these we intuitively know because we're familiar with this set. We've used it for a long time. If I take ax plus b, if I multiply it by 1, yeah, that's going to give me ax plus b back. So multiplication by 1, that checks out. What about closure under vector addition and under scalar multiplication? If I take ax plus b and add cx plus d, they get a plus cx plus b plus d. That's going to be in, oh, that's a linear function. It's some number times x plus some number. That's exactly what it means to be in set L. It's a linear function. So yeah, it is closed under vector addition. If I take any two linear functions in the set and add them together, I still have a linear function. It's still in the set. Same thing for closure under scalar multiplication. If I take any element in the set ax plus b and I multiply it by k, distribute, I get k times ax plus k times b. That is still a linear function. It's still some number times x plus some number. That's what it means to be in this set. And so it checks out. So every one of these properties checks out, which means in this abstract sense, L is a vector space. Okay, and it means we can call all the elements of L vectors in this vector space. Okay, so for example, 2x plus 3 is a vector in vector space L. In this abstract sense, it is vector because it's going to have all these properties that we're used to for our vector space Rn. So it's going to behave very like it, and it's going to have a lot of those same properties.